In this first sublesson, we're going to cover interdomain concepts. From our objectives list, we're going to talk about an introduction to autonomous systems. We'll talk about internal versus external gateway protocols, and we'll talk about trusted versus untrusted peering. Let's start off by asking the simple question, what is an autonomous system? You've certainly heard that term before, but it means different things in different contexts. For example, OSPF uses the term autonomous system, but in that context it refers to the boundaries of the OSPF routing domain. In the context of BGP, we mean something very specific. Here's a definition. An autonomous system is a set of routers and networks under the control of a single administrative authority. Autonomous systems allow the separation of administrative domains. IGPs, interior gateway protocols, run within an autonomous system, and IGPs route between nodes within that autonomous system. An illustration will help. Here we have a set of routers, fairly well meshed, and all running a common routing protocol. But imagine that many of these routers are under the control of different administrators. Most routing protocols will run fairly well in this network, but suppose this network grows by an order of magnitude or more. In that case, a single common routing protocol will no longer scale. And even in the size shown here, trying to apply consistent routing policies among many different network administrators becomes impractical. And lastly, trying to schedule coordinated upgrades, for example, to add new features to the routing protocol, become impossible to schedule among more than a handful of different administrators. These are the problems faced by the builders of the ARPANET, the predecessor of the modern Internet. Their solution was to segregate the different administrative domains and call each separate domain an autonomous system, a network system that is administratively autonomous. Now policies can be applied between and among autonomous systems while the individual administrators have the freedom to run their individual domains as they see fit. For instance, each administrator is now free to choose his or her own IGP according to the needs of their own network and their own preferences, completely independent of what an administrator in a different autonomous system might be doing. So, for example, in this illustration, you can see that some administrators are running EIGRP, some are running ISIS, some OSPF, and in at least one case, RIP. You can also see that an autonomous system is running both OSPF and EIGRP. A single AS doesn't prohibit you, if you want, from running multiple IGPs within it. Returning to our definition, you've seen that IGPs run between nodes within the boundaries of a single autonomous system. EGPs, external gateway protocols, route between autonomous systems. And in modern IP networks, BGP, Border Gateway Protocol, is the only EGP in common use. You can think of BGP as the routing protocol of the Internet. BGP routes among autonomous systems. In our illustration, you can see the individual autonomous systems running their own IGPs internally and using BGP to exchange routing information with neighboring ASs. So to re-emphasize, we have internal routing protocols and external routing protocols. These two terms are from an autonomous system perspective. If BGP is going to route among autonomous systems, it must have a way of uniquely identifying each AS, just as, for example, OSPF requires a router ID to uniquely identify each router. That's the job of the autonomous system number, some examples of which are shown here. An autonomous system number is 16 bits long and is assigned and managed by the regional Internet registries the same way an IP address is assigned. Some quick arithmetic tells you that a 16-bit space gives you decimal numbers between 0 and 65,535. These numbers are divided in special ways. Numbers 1 through 64,511 are public AS numbers. 64,512 through 65,534 are private AS numbers. These private AS numbers are intended to be non-unique and can be used over and over the same way you use private RFC 1918 IP addresses. AS numbers 0 and 65,535 are reserved. Now, there's some concern about the 16-bit size of the autonomous system number space and whether it'll continue to serve the needs of the growing Internet with sufficient available AS numbers. As a result, there's a newly defined 32-bit autonomous number format. That new format is not yet in widespread use, and so it's discussed here only marginally in this course. But if you want to know more about them, you can read about them in RFC 4893. Now, when I say that BGP routes among autonomous systems, I mean, of course, that routes leading to some set of destinations are being exchanged between the ASs. These destinations are represented by address prefixes. The prefixes I've shown in this illustration are very generic. Prefix A, prefix B, prefix C, and so forth. In BGP language, these destinations or these prefixes are called Network Layer Reachability Information, or NLRI. You'll hear that term quite a bit more in this course. The prefixes that we deal with in this course are IPv4, but the generic prefixes shown in this illustration are put there to emphasize the fact that BGP can carry more address types than just IPv4. When BGP advertises other address types, called address families, it's called multi-protocol BGP. We don't discuss multi-protocol BGP in this course, but I wanted to at least make you aware of it. I want to re-emphasize the important difference between IGPs and BGP. IGPs find paths between routers. BGP, on the other hand, takes a higher perspective of the entire internetwork. Rather than paths to destinations through individual routers, BGP finds paths to destinations through autonomous systems. So IGPs are intra-AS protocols, and BGP is an inter-AS protocol. Another important contrast between BGP and IGPs is the idea of trusted versus untrusted peering. IGPs assume that their peers are trusted because they are all under the same administrative domain and are controlled commonly. So IGPs tend to view route information holistically. That is, every router has an equal job to do, and the protocol is designed for easy exchange of information. BGP, on the other hand, assumes that its peers are untrusted because they're controlled by some other administrator. Therefore, route information is exchanged very carefully under BGP. Each BGP peering is also controlled and configured separately. Incoming and outgoing route advertisements are also viewed separately. Here's an illustration that might help with that last concept. From the perspective of router 1 on the left, it might have outgoing BGP advertisements. Those outgoing advertisements influence incoming packets. At the same time, router 1 might be receiving incoming BGP advertisements from router 2. Those incoming advertisements influence outgoing packets. The point is, BGP can be configured to carry advertisements only in one direction, incoming or outgoing, or it can be configured to exchange advertisements in both directions. An individual BGP advertisement can associate a number of so-called path attributes with a prefix. Path attributes enable BGP routing policies, sometimes quite complex routing policies. We'll talk about routing policies beginning in Lesson 7.